Hi everyone, it's John again. So we're just going to be going over the next worksheet this week. Hope this helps. So starting with problem number one, it says convert each pressure to atmospheres. So general conversion that you're going to want is that 1 torr is about equal to 1 mmHg. And then you also want to know that 760 mmHg is equal to 1 atm. Also 101.3 kilopascals is equal to 1 atm, and 1.013 bar is equal to 1 atm. Now notice how the kilopascals and bars are the same numbers, just that the decimal is moved over. So 1 bar is, or sorry, 100 bars is 1 kilopascal. Numeric wise. All right, so then we can convert each of these. So it's pretty straightforward, just using your conversions like we always did. So you start with 736 mmHg. We want to go to ATM, so 1 ATM over 760 mmHg. And then when you plug that into your calculator, you should get 0.968 ATM. And that's for A. For B, you're doing the same thing, right? These are all just conversion problems. So for that many bar, there's 1.013 bar in 1 ATM. Plug that into your calculator, and you should get 0. It's going to be really the same, 766, about the same ATM. For C, doing the same thing, 892 torr. For every 1 ATM, there's 760 torr. You plug that into your calculator, you get 1.17 ATM. And then for D, you're doing the exact same thing. Just using conversion factors to convert between units. When you plug this in, you should get 2.2. All right, next it says calculate the height of a liquid column of liquid glycerol in meters required to exert the same pressure as that. So in general, your formula is going to be the pressure due to a column is equal to the density of the liquid times gravity times height. That's the formula we're going to use. So first, what we want to do is figure out how much pressure is exerted by the carbon tetrachloride column. So how do we do that? We can say the pressure exerted by the carbon tetrachloride is equal to the density of the carbon tetrachloride times gravity times the height of the column, which is, so one thing you do want to be aware of is this is in grams per centimeter cubed. We're going to want this in terms of meter cubed, kilograms per meter cubed. Actually, grams per meter cubed works fine too. So this is 1.59 times 100 cubed. So using a conversion factor, convert from centimeters to meters cubed. I won't write that out just because out of space here, but that's all that part is. It's a conversion. Times 3.02 meters for the height times 9.8 meters per second squared. Right, the reason we want this in meters is because these other things are in meters. Okay. Then when we go ahead and plug that in, we should get 4.71 times 10 to the 7th And then this should be in pascals. Okay. Actually, wait a second. This is in grams, not kilograms. So this is actually in millinewtons per meter. You don't have to keep track of the units, but it can be nice. So if you wanted this in pascals, you'd have to make sure this is in kilograms. Okay. Then we go ahead and plug this in because we know that the pressures are the same. So we're plugging this into the formula for glycerol because we know the pressure of glycerol due to the glycerol column is going to be equal to the density. Oops. Times gravity times the height, which is what we're solving for. You do a little bit of algebra, right? Just divide both sides by 9.8 and the density, 1.26 times 100 cubed. And then we get the height of the column. When you plug that in, you should end up getting 3.81 meters. And that's it. For number 3, it says simplify the units. Hint, when you simplify these units, what unit of measurement are they equal to? So you've probably seen quite a bit of unit analysis by now. So you can say this is equal to meters squared over seconds squared. So taking these front two first, times kilograms over meters cubed. Meters cancel out. Then we're left with kilograms over seconds squared times meters. And then, yeah, so that could be it for this. But this is also the unit of pascals. So pascals, the reason it's a unit of pascals is pascals have units of newtons per unit area, which is kilograms times meters per second squared, right? MA from Newton's second law. So that is the unit of pascals, right? And the right side is just kind of double checking. All right. Then we have the kinetic molecular theory of gases. So let's calculate the root mean square speed in meters per second for Cl2 molecules at 30 degrees Celsius. So the formula for this, it's often called ERMS. That's how people say it. Is equal to the square root of 3 times R, oops, one of our constants, times T over the molar mass of the molecule. T is in Kelvin. And then R is 8.314 joules per Kelvin mole or mole Kelvin. So we go ahead and plug this in. 3 times 8.314 joules. I mean, I'm just going to leave out the units. Times 303.15 over, and then the molar mass. So the thing about the molar mass you have to be careful of in this formula is molar mass must be in kilograms per mole. So on the periodic table, you have grams per mole. But the molar mass has to be in kilograms. So you're dividing by 1,000, essentially. Okay. And then you plug this in and you get 327 meters per second. And that's it. 70.9 I got from chlorine on the periodic table. Adding those up. At what temperature will the root mean square speed for neon be the same as helium at 300 Kelvin? So first we start off with helium. Same formula. Then we plug in 3 times 8.314. So there's just a lot of formulas in this unit. 300 Kelvin, 273. Oh, no, wait, no, it's Celsius. So that's just 300. Helium has a molar mass of 4. And we want this in terms of kilograms. So we divide by 1,000, right? Helium has a molar mass of 4 grams per mole, or 4 times 10 to the negative third kilograms per mole. When you plug this in, you get 1,367 meters per second. And then we can do it for neon. So we know that the root mean square speed of neon is equal to the root mean squared speed for helium. Then we can plug in these things. Um, Neon has a molecular weight of, or molar mass of 20.18, 20.18 divided by 1,000 to convert to kilograms. That's the most common mistake that you'll see on a test, or that you may make, is not converting to kilograms before using this formula. You solve for t here algebraically, you get 1367 squared. So you square both sides, multiply both sides by the bottom or the denominator, then divide by the things multiplying by t. And then when you plug this into your calculator, you get 1510 Kelvin. And this makes sense because for neon to go the same speed as helium, you need an elevated temperature because the molecules are heavier, right? The neon atoms are just heavier than helium, so they need more energy to go the same speed. On average, go the same speed. Then it says determine the mode, the average, and the root mean square for a group of 10 automobiles blocked by radar speeds of that. So the mode is just the thing that comes up the most. So we see 255s. That comes up the most. So it's 55 miles per hour. It just comes up most. Then the average. You're just summing them all up. Then you're dividing by how many there are. Right, just by definition of your average. Then when you plug that in, you get 45.5 miles per hour. And then we can do our root mean square. So where does the name root mean square come from? We're taking the square root of the mean of squares. So you're squaring each term. Then you're averaging them. So root of the mean of the squares. You plug this into your calculator, you get 40.7 miles per hour. So root of mean of the squares. All right, then that's it for this. Next, we have a lot of multiple choice. It says, in which of the following cases is the gas most likely to behave as an ideal gas? So something that behaves as an ideal gas at high temperature, low pressures. So that way you don't have these molecules that are not moving very quickly around or being compressed together by a high pressure, where you have these kind of attractive or interactive or repulsive, whatever, but interactive forces between the molecules and atoms. So let's see which one fits out the best. Well, we have for A, water at 375 and 750 torr. So that's about 1 atm. Then we have B, helium at set 37.5 Kelvin. That's very low and very high pressure. So it's not going to be B. C, it says we have methane at 37.5 degrees C. That's about 305 Kelvin and 7.5 atm. So that's a high pressure. So that's also not going to work. Again, let me just write this in. High temperature, low pressure. Same thing with E. It's just a low temperature or lower than some others. So we're really between A and D. D, you have a lower pressure than you do with A um, and a higher temperature. So the answer is going to be D because 375 Celsius. So A probably also acts like an ideal gas, but we're just looking at which is most likely. So highest temperature, lowest pressure. If someone were to light a cigar at one end of a closed room, persons at the other end of the room might soon perceive an odor due to gaseous emissions from the cigar. So this is an example of diffusion. So diffusion is where you have uh, particles move from one place to another, or more specifically, they move from an area of high concentration to an area of low concentration. So one example of diffusion, right, is like this. So a cigar, or if you spray Febreze or something like that, an air freshener in your room, you have a high concentration wherever you spray it, and then it slowly spreads out throughout the room. Uh, and that is diffusion. That's the process of diffusion, going from a high concentration to low concentration. For number 9, it says if a liter of CO2 is compared to a liter of H2, both at 25 degrees C and 1 atmospheric pressure, then we're going to check the true or falsity of each of these. So they do not have the same average speed. This is not true because it's dependent on the molar mass. They have the same average kinetic energy, but they do not have the same average speed, right? It's dependent on the weight of the molecule or the mass of the molecule. So it's not A. You can look at your root mean squared formula. You're dividing by molar mass, you divide by a bigger number, you get different numbers. CO2 is going to be slower than H2. B is wrong from PV equals nRT. You have two gases at the same pressure, same temperature, and the same volume, then you're going to get the same moles of each gas. C, it says the average kinetic energy is greater for CO2. That's not true. As I just said, the average kinetic energy is the same. The answer is D. The CO2 molecules are on average moving more slowly than the H2 molecules. So heavier the molecule is, more mass, the slower it goes. You can relate this to physics with your kinetic energy equals 1/2 mv squared. So given some kinetic energy, they're the same for the CO2 and H2. The larger the mass, the smaller the velocity is. Then E, it says the mass of 1 liter of CO2 equals the mass of 1 liter of H2. Um, Not true, right? 1 liter of CO2 will weigh more. All right, 10, it says according to the kinetic molecular theory of gases, uh, gaseous particles are in constant nonlinear motion. At a constant temperature, all particles have equal translational kinetic energy. So that's, oh, sorry. So for A, that one is not true. They could be moving in linear motion, could be nonlinear motion. They're generally in constant motion, but it doesn't have to be nonlinear. It doesn't have to be linear, but they are in motion. B, it says at a constant temperature, you have translational kinetic energy, so moving. That's not true. It's the average kinetic energy of all particles of different types of gases are the same. Any two particles in your space, whatever it is, or your container, are probably not going to have the same kinetic energy. One may be moving very slow, one may be moving very fast, but on average, they have some sort of average. Um, Most of your particles are going to be around the average, not at the average, but around the average. You can think of it as kind of like a Gaussian or a bell curve, where this is kinetic energy, this is number of particles, and like something like that, where most particles are here. But not all. Whoa. So most particles are going to fall in that realm of the kinetic energy where the mean is, or the middle of the Gaussian, but not all of them, right? There are also not all the same. And then for C, it says the faster a given particle is moving, the greater the translational kinetic energy. That's true. That just goes with velocity. More kinetic energy you have, the faster it goes. Um, for D, it's not true because it's a function of temperature, not volume. And then E, it says all interparticle collisions are inelastic. That's not true. If you don't know what elasticity is, I wouldn't worry about it. Has to do with physics and collisions. All right. Number 11, it says the volume correction term in the van der Waals equation is present because what? A, barometers are inaccurate. Uh, B, molecules are diatomic. C, molecules attract each other. D, molecules occupy volume. Or E, molecules repel each other. Intuitively, with the name, the volume correction term in the van der Waals equation is because molecules occupy a volume. So they can't overlap with each other. Um, yeah, that's it. So that is what the correction term does. So they're not infinitely small particles, they occupy some space, and that affects how they interact and where they will be in relation to each other. 12, it says if gas volume is doubled, but the temperature remains constant, then A, the pressure stays the same, the molecules move faster, um, kinetic energy increases, the molecules move slower, or none of the above. Um, so if you, we're going to have to check all of these. So if you're checking for the pressure, we can use Charles' law. And compare the final pressure and initial pressure. So it says the volume is doubled, but the temperature is constant. So T1 is equal to T2, V1, um, volume is doubled. So V2 is equal to V1. So twice the volume. Then we plug this in. And then you're going to get a relation that shows that P2, so both sides, T1 cancels out, right? And V1 cancels out. And if I want to see P2 in terms of P1, is you get half the pressure. So because you get half the pressure when you double the volume and keep the temperature the same, it can't be A. B, it says the molecules move faster, or the kinetic. So if molecules moving faster and the kinetic energy increasing go hand in hand. So how do you look at that? You can look at your Erm's formula. Right? So if you're looking at this tells you your root mean square speed of your molecule. So your average speed. Well, R is a constant. E is the same. The molar mass is the same. So the speed is not going to change if you double the volume. And because the speed is not changing if you double the volume, neither of those work. All right. Then we have D. It says the molecules move slower. So I should actually encompass that one too. And then the answer is none of the above because they don't move faster or slower or change their kinetic energy if you double the volume, and the pressure does change. It has. All right. 13, it says calculate the average kinetic energy, EK in joules per molecule for O2 at 298 Kelvin and 1 atm. You want to calculate the average kinetic energy per mole. You're going to use this formula. And there's a reason I'm saying per mole, because of this problem, we're asking for per molecule. The formula is 3 halves RT. That's it. Where R is your constant, 8.314, and T is your temperature in Kelvin. So if you plug these in, 3 halves times 8.314. I'm going to keep mine over units here this time. This is joules per mole Kelvin. T is 298 Kelvin. You'll notice that the Kelvin cancels out. I should probably label it like that, KE average. This is going to give you 3,716.358 joules per mole. Now we want joules per molecule. So what do we do? Well, if we want to go from mole to molecule, as you're all familiar with, should be familiar with by now, is we're going to use Avogadro's number to convert from something from moles to molecules, because I want this in joules per molecule. So for every one molecule, how many joules of energy is there? So I'm going to use Avogadro's number here. So for every 1 mole, I have 6.022 times 10 to the 23rd molecules. And then we get 6.17 times 10 to the negative 21 joules per molecule. So every O2 has 6.17 times 10 to the negative 21 joules of kinetic energy. All right, 14, it says the energy of molecules of a gas is what? Dependent on concentration. So, I mean, we just saw the formula. So the average kinetic energy is just dependent on temperature. So it says it's distributed over a wide range at a constant temperature. So this is true. It's not the same for all molecules at a constant temperature. So C is not true. It increases with a decrease in temperature. That doesn't make sense. Increase in temperature is increase in energy. And then E, it does not depend on pressure at all. So the way you can think of B is you have this Gaussian. So you have your number of molecules with some kinetic energy on your y-axis. You have kinetic energy on your x-axis. And it's going to look something, probably something wider. Really depends on what you're looking at. So most of your molecules are around the average, but not all of them. So they're distributed, right? If you could have some molecules moving fast, some moving slow, but most of them are going to be around the average, right? It's a Gaussian distribution is what it is. So they are distributed among a wide range, but they're mostly around the average. Gas laws. 15 says a sample of gas has a volume of 4.25 liters at 25.6 Celsius and 748 milligrams of mercury. What will be the volume of the gas at 268, 226.8 Celsius and 742 mmHg? So first thing you want to do is I would convert these all to ATM and then use them in Charles' law. I don't think it's actually necessary, but I'm going to do that anyways. I'm not going to write out the conversions since we did that in the beginning. I'm dividing by 760 here. This is 0.976 ATM. There's 748. That's 0.984 ATM. And then for kelvins, I have 25.6 degrees Celsius, 273.15. It's 298.75 Kelvin. And then for 26.8 degrees Celsius, we have 299.95. Now you do have to convert these to Kelvin. So make sure you do that. If they're not in Kelvin and you try using Charles' law or the other laws, Boyle's law, whatever else, you are going to get the wrong answer. So make sure you have these in Kelvin. Then we can plug this into Charles' law. I think that's Charles' law. So this first one, 742 was P2. That was P1. This is T2. This was T1. And then I just have to plug in everything. So before I even do that, I'm going to algebraically solve for what I want. V1 is 4.25. So I want to find the final volume. I'm going to do that because it's going to get messy if I just move around a bunch of numbers, and I really dislike doing that. So I'm going to algebraically solve here for V2. So that way I can just plug in everything now. So now I can plug in everything for V2 and make my life easier. So I have 0.984 times 4.25 times 299.95 divided by 298.75 times 0.976. And the volume I got to be 4.30 liters. And that's it. All right. Next says, what is the molar mass of monochloroethylene, which has a density of 2.56 grams per liter at 22.8 degrees Celsius and 756 milligrams of mercury? How do you do this one? This one's a little bit hard. if you don't know your formulas. So first we start with PV equals nRT. Now this doesn't tell us anything about density um, or volume. It makes you don't even have volume, right? And it doesn't tell us anything about molar mass. Um, so what do? Well, we have N in there, and N stands for moles, right? Now recall that mass is equal to moles times the molar mass, correct? So what we can do is this. We can say mass is equal to moles times molar mass. Then we get the moles is equal to mass over molar mass. Now I have a relationship that I can plug in for N that I have the molar mass for, right? So you take an equation, you look for things that you already know or things that you want. So in this case, the molar mass. And then I try to remove a variable and replace it with something with the thing I want, right? So molar mass here. And N is the only thing that relates to molar mass in this whole equation of PV equals nRT. So I have that. Now this still doesn't really help because now I don't have mass, right? So if I want to get rid of mass, well, I know mass and density relate to each other. I don't like using a small d here, as you'll see in a second, but I think that's the convention you are using, so I will stick with it. Density is equal to mass over volume. So mass is equal to density times volume. Note how I don't like the density because dV is often a differential in calculus, but so I'm making it very clear there's a dot between them, d times v, or density times volume. So then I can plug in to the moles, and I get d times v over molar mass is equal to moles. Then I can plug this in into PV equals nRT. Let me actually say here. And we get PV is equal to, so N is D times V over molar mass, RT. Now we can solve for the molar mass. So note how the volumes cancel out. So P is equal to D over molar mass, RT. And I'm just going to solve, I'm going to solve for molar mass here, which is going to be density times R times T over pressure. Now we have everything that we need and we can just plug it in. So density is 2.56. I'm going to write down my units just to make sure I'm not messing this up. R is 8.314. Oops, no, wrong one. 0.0821. And then this is an ATM per mole Kelvin. Oops. And then we have Kelvin, which is just 22.8 plus 273. 295.95. Not running out of space. Oops. And then divided by the pressure. So I'll just convert it right here. 756 mmHg. And then convert to ATM. Now I actually did forget a unit here. This is ATM times liters per mole Kelvin. Now, if you do this all, you'll see everything crosses out. So these liters cross out, these ATMs cancel out. These kelvins cancel out, and then you're left with grams over moles. Then we end up with 62.53 grams per mole, and that is the molar mass. All right. Next, 17, we have if gas volume is double, but the temperature remains constant. We saw something similar to this. So if you're using, so the kinetic energy stays the same. Let's just note that. So the average speed is also the same. Okay. So volume is doubling, the temperature is the same. We can use this one. It's like Charles' law, except the T's are the same. I just always use Charles' law because it's easy to remember, and if things are the same, they just go away. So P1 V1 is equal to P2 V2. We know that the volume is doubled. I think we actually saw this before. And it should have the pressure. So the pressure does not stay the same. Molecules do not move faster. The final pressure is not twice the pressure before the volume change. It's half. Molecules do not move slower. It is 1/2. All right, last page. It says a mixture of 4 grams of H2 gas and 10 grams of helium in a 4.3 liter flask are maintained at 0 degrees Celsius. What is the total pressure in the container? So what we can do here is first, we're going to use PV equals nRT, where N is total moles of gas. So you could use PV equals nRT and find the partial pressure of each gas first, and then just add them up. I'm just going to do the total. There's multiple ways you can do this. I'm just going to do it like this because A is asking for the total pressure first. All right, so 4 grams of H2 is about 2 moles of H2. Right, 4 divided by 2. And then 10 grams of helium is about 2.5 moles of helium. Since helium weighs 4. So we add these up. There are 4.5 total moles of gas. And then we can plug this into PV equals nRT. Write that over. So P, and then we have pressure. Oh, no, we don't have pressure. So P is equal to nRT over V, just solving for P, so I don't have to rearrange numbers. And then we have 4.5 times 0.0821. Note how the constants are different from like erms. And then T is 273.15 at 0 degrees Celsius. And then the volume is 4.3 liters. And you plug this all in. And we get 23.47 ATM. And that's it. All right. Moving on to the next, we have what is the partial pressure of each gas? So the way you can do this is take your total pressure and then multiply it by the molar ratio of each gas. So the partial pressure of each gas, again, molar ratio, I mean moles of certain gas divided by total moles of gas. So we can say the pressure of each gas is proportional to their moles or to the amount of moles divided by total moles. So 23.47 is our total pressure, right? We can even say it like this. P total is equal to the pressure hydrogen plus the pressure of helium. The pressure of hydrogen is equal to the total pressure times the moles of H2 over the total moles. Then all we do is plug in. So total pressure is 23.47 atm. Then there are 2 moles of hydrogen. There are 4.5 moles in total. So hydrogen contributes a little less than half of the total moles. And then we get 10.43 atm. You can do the same for helium. You can also subtract it from the total here. Either way works. I'll just stick with this because I think most people follow this easier. I would just subtract it from the total at this point because there's only 2 things that make it up. And then this is moles of helium over the total moles. Pressure of helium is equal to 23.47, 2.5 over 4.5. And then we're going to get 13.04 atm. So notice how it doesn't matter how big the molecules are. It just depends on how many moles of the molecule there are, and that contributes to pressure. So pressure is determined by how many moles of gas you have, I mean, as well as temperature. But assuming a constant temperature and volume, it just depends on moles of gas. It doesn't matter what kind of gas it is. It doesn't matter if it has a large molar mass or a small molar mass. At least according to ideal gas law. All right, number 19. Says a gas cylinder of 53.7 liter volume contains N2 at a pressure of 28.2 atm at that temperature. How many grams of neon must we add to the same cylinder to raise the total pressure to 75? So we know the total pressure is the pressure contributed by nitrogen gas plus the pressure contributed by the neon we want to add. So the pressure of the neon we want to add is going to be equal to the total pressure minus the pressure of N2. Now you could just plug this in. It's going to end up being 75 minus 28.2. I'm still just going to leave it like this for now because I want to plug in everything at the end. You know what? Fine. To make it more clear, I won't do that. I like to usually solve in terms of variables, but I'll just plug this in now for all of you watching, in case you don't like that. So we plug this in, 28.2. We have 46.8 atm. So that is the pressure of neon we want. Then we can go to PV equals nRT to find the moles of neon that we want, right? So the moles of neon we want is going to be equal to, oops, well, the pressure contributed by neon times the volume of the container divided by RT by algebra. You can plug this in. The pressure is 46.8. The temperature is 299.15. R is 0.0821. And then temperature is 290. Oh, wait, temperature. Sorry, 299.15 is the temperature. The volume is 53.7. Then you can plug this in. You get 102.33 moles of neon. And then we convert to grams with molar mass. So the molar mass of neon is 20.18. So you divide by 20.18. And we get 5 grams or 5.07 grams of neon. And then that's it. Yeah. Oops. Why did I divide? Sorry. Multiply. Grams is equal to moles times molar mass. Yeah, 5 is way too small. Let's see. 2,064.95 grams of neon. That's also why you should write out your unit conversions. It's easy to make mistakes, simple mistakes like that. All right. 20, it says a 31.4 milliliter sample of nitrogen gas was collected over water at 23.7 degrees Celsius and a barometric pressure of 706 milligrams of mercury. What mass of nitrogen was collected? So for this one, the way this is like set up in a lab, just to simplify it, you have some tube, you have some bubbles, you have N2, this is too small. I'm going to enlarge this picture. So you have some reaction happening that's creating nitrogen gas. So something down here is reacting and it's creating nitrogen gas. And it bubbles up here. So now you have nitrogen gas particles. But you also have particles from the water turning into a gas. So some of these water particles turn to a vapor, like that. And now what you're doing is measuring the pressure. So there's a barometer, and it measures pressure. So that's the experimental setup, right? It's measuring the pressure inside. Right? Somehow. So what you can do is you can say that the total pressure here, measured by the barometer, is equal to the pressure of the nitrogen gas in there. And you're assuming there's no other gas. Pressure of the nitrogen gas plus the pressure of the water. So what we do here is we're solving for the pressure just due to the nitrogen. So when it says vapor pressure of water, this thing, that's P of H2O in this formula. So the pressure of nitrogen is the total pressure minus the pressure of water. So 706 minus 22 is 684 milligrams of mercury. Then we can go ahead and plug this into PV equals nRT. This is for mass. We get N is equal to PV over RT, like we just saw before. Or you can say N is equal to mass over molar mass. That way I don't want to have to write out the step afterwards. You can do the conversion after if you would like. And then I can just plug in everything here. So the pressure is 684 mmHg. So I need to convert this. That is the pressure. The volume is 0.31.4, so 0.0314 liters. The molar mass of N2 is 28, about. Then R is 0.0821, your constant. And then T is 23.7 plus 273.15, which is 296.85. After plugging in, you get 0.0325 grams. And that's equivalent to, if you multiply by 1,000, 32.5 milligrams. And that is your answer. All right. Well, I hope that helps. And I'll see you in the next one.